Hello everyone, welcome to High Performance Computing, Advanced Scientific Computing course. This is lecture 10, OpenFoam software and CFD applications. We are following the outline of the course, which is this year it's CFD special, and in the lecture 10, we will have a short lecture for OpenFoam software. To have a short recall from the previous lecture, lecture 9, we take a look at the application of the CFD, which is specific categories. It's called RANs, LES, and DNS for turbulent flow. And we learned that it's required to have access to the HPC to run such simulation. Because of the complexity in nonlinear and large computation in the turbulent flow. And also we talked about the different of the capability between these methods when we are using the RANs and when LES and DNS. Especially DNS was costly and usually used for the research and development. In the industry, the most applicable method is the RANs. We also presented the MPI application in CFD and how we can decompose the domain of the problem between different processors and what's the matter about the boundaries between the processor to transfer the information between them. Now let's move on to this short lecture. OpenFoam is the open source software. It's used in the fluid dynamic area, and since it's free and open source, we can have a new design of the problem with the domain, with the boundary condition, and write a new problem and also write a solver for it and make modification to use with high performance computing. We will have introduction to this software, which is open source, and how we are doing the decomposition method, how the MPI and decomposition relevant to these open source code. And I will try to show you a practical example on the HPC system and how you can set up your batch file. Then OpenFoam is open source code, and you can see the presentation of the official web page of this software. You can find the good information about this software, and it's working in the fluid dynamic. As we said, we have different type of regime of the flow. Laminar and turbulent, it's working for both of them. Also, we can use it for compressible and incompressible flow. And it has this ability to run the parallel computing, which is important part of the simulation in the CFD. In fact, everything for the setup for the solving the problem, it's going regular. You need to have a geometry of the problem and the properties of the material, information about the boundary condition and initial condition. Then in one setup, you need to define the parallel computing, which has a different approach. Then when we're running the solution, based off of this setup, the problem will be solved in the parallel with a number of the codes that we are defined and the process. Regarding OpenFoam language and algorithm, it's used in this software. It's working with a C++ toolbox, and it's possible to customize the numerical solver. In fact, it is possible to create a code for the specific problem in the laminar flow, turbulent flow from the scratch, and you specify the problem domain, everything, the geometries, and the condition of the problem with its toolbox language and create a new model and run it. So this is the most thing that the researcher for the new problem they are doing, and this is a great capability that OpenFOAM created because it's connected to the visualized software. We can have the visualization. We will talk them in the next slide. And also it has capability to run in parallel. In the OpenFOAM, we can have the pre or post processing and also doing the solution for continuum mechanic problem, which is mostly the core application. It's on the computational fluid dynamics CFD. In the industry also, some example we can mention here regarding the automotive, manufacturing, process engineering, environmental engineering, they are using it. On the basics physics study also, there are some simulation used in the fluid dynamic doing the simulation and maybe to understanding the uh, internal processing of the turbulent flow. In fact, to mention the CFD capability, maybe it's good to point to it. In fact, in the fluid dynamic, as we said, on the turbulent flow, there are different approaches used. One of them experiment, and one of them analytical, or in the turbulent flow, mostly we can say statistic and deterministic method. And the another one is the CFD. In fact, CFD helping us to deal with some problem and get the solution, but it doesn't provide us the um, processing that going in the structure of the phenomenon. Therefore, it's really helpful and significant result is presenting in the industry. But to study the physics of the problem, it's helping with this visualization to understand what's going in the a specific problem based on the domain and the initial condition and boundary condition. Also, OpenFOAM as a software has its structure. In fact, there is a part of libraries and directories we can use and doing the setup for the problem. As we said, based on the C++ language, it is possible to do this. There is a standard solver used in this software, and also we can define solver based on our problem. And we talked about it since it's open source, so it's uh, flexible to have a new setup and a new application, uh, which make it a great option to study the fluid dynamic area. And we will mention that some capability of this solution when it's visualized by the PowerView software, it makes it great to present the result. Here you can see the list of the libraries and directories which is used on in the OpenFOAM simulation. In fact, it's depend to the user selection, and it could be additional directories. Uh, they are the standard one, the system, constant, and zero, which is mostly used for the initial time directory. There could be more directories, which, for example, the result time directories and about the post processing, which mostly relevant to visualization. And we will see how it's working with the specific visualization software, which is as a third party connected to the OpenFOAM. For OpenFOAM, usually we are using the PowerView. Is free and has a modification and compiler and customization, uh, which we can use it with its command on the OpenFOAM. We can present the result. We can make a post processing, and also it's capable to run it on the HPC resources, which is also open source software. So far we see the OpenFOAM its own open source, and we can make modification, and we can have a new uh, setup for our problem and capable to run it on the HPC. When we look on the visualization also, which is PowerView, it's open source, and we can make a modification and compile it. And also it's run on the HPC. Why it's important? Because some visualization in the CFD, when we are working especially with the large problem or with a complex problem in the turbulent flow, the result will be massive data. And to run these visualization on the software, it's required to have access to the HPC and power of the graphic to present these results. To make parallel computing and HPC application for the CFD, this is a reminder that we presented in the previous lecture how the parallel computing is working for the specific domain of the problem. We need to make a decomposition of the problem, and here we can see how the number of the storage which is required, and also we talked about the overlap between the subdomain, which is important because the boundary condition, the boundary data need to have interchange in this area, especially when we have unsteady problem. And during each time step, it's required to update the information from the neighbor subdomain to perform the solution and get the result. And we talked regarding this matter in the previous lecture, so we can understand how the parallel computing is working on the uh, uh, OpenFoam software. And here the presentation is 2D. So imagine if we have 3D problem, we will have decomposition of the 3 dimension problem based of these information. So the overlap, it will be not a point, it will be like a surface between different subdomain, and it requires to uh, transfer the information between them. And on the surface, of course, we have many grid points which require to have the possibility to update every time step. Regarding the MPI that we talked in previous lecture, it's important to use these uh, capability in the HPC to have efficient HPC computing and also keep the accuracy of the solution. Here is example from result for lead driven cavity flow with MPI. In this figure, there are results from the ideal scaling, MPI and MPI plus OpenMP that we can see. In the left hand side, it's for single node application with the domain of 200 times 200 200 cell, which is used, and we can see how when the number of the core increase, there is a difference between the ideal scaling and MPI and OpenMP. And the OpenMP plus MPI and MPI, they are very close to each other. But in the right hand side, it's used for example with 100 times 100 times 100 cells with multiple nodes. And we can see when there is an increase in the number of the core, the ideal scaling, MPI and MPI plus OpenMPI, they are close to each other. And in fact, the ideal scaling also is getting like linear behavior, and the MPI, it's getting similar. However, from the specific number of the core, they getting a different result. Uh, that's why it's important to uh, select the efficient setup for the MPI, in the CFD and able to m- make the efficient running of the parallel computing with accurate results. Then regarding the decomposition and the subdomain need to created for the domain of the problem and example of the MPI that we talked about it. The decomposition method in the OpenFOAM is available in the standard form. We can say that only we can run it with its command. There is a one. It's called simple, and the hierarchical one is coach, and the manual which need to be set up by the user and make a modification. We will present them on the code, and you can see how they are working and they are effective to make the simulation. In fact, each one has a different decomposition setup uh, on the domain, and the selection of these different methods, it is a knowledge about this structure, that how it makes the decomposition, because based on the geometry sometimes we have symmetric geometry, sometimes no, and sometimes the geometry it's have a bad shape, or we can say on the meshing also sometimes we are dealing with structured unstructured one. Then it's required to select the um, best one to have a, efficient solution in the HPC and also proper result. To have example of the parallel running for the OpenFOAM, I will share this batch file on the lecture. You can use it and you run example of the OpenFOAM in parallel. Regarding the setup on this batch file, as you know, and you modified the other batch file in this course, on the second line you need to specify your email, and since you have access to alias system, so we'll use the partition on the Uton as we specified here. The other setup is fine. You can see the number of the node. Of course, to see the computation, you can use different number. Here the node is 1, and you can change it. The task per node also is specified 4. You can change, of course, which is relevant to the number of the MPI task. Also, you can change the memory if you think the maximum time of the running here is 4. It depends the queue that you when you submit the work. And you can also here we specify the file for the output and also for the error. In the next section of this batch file, you need to specify directory for the simulation that you want to run. Here the address is specified, the directory is specified for the file that I'm using. You need to specify it based on your directory, because of course every person has his directory on the area system. You take a copy from the file and you can use it there. Regarding the open file example, you will see in the next section how is it. The module that you need to load to run this simulation here is specified. Please pay attention. Sometimes maybe you will run it. If you get error about the modules, you can check it with the administrator of the system. They will tell you maybe there is some update. You can ask them, and it will be resolved. But currently, it's working with this module. Then you use the common source of the form batch, which is required here. Then you make a copy from the file, which is available in the directory of the form tutorials, from the incompressible example, simple form, and pit daily. This command will make a copy from this file, and then you will use the command to uh, copy this file to your directory. To run the simulation, firstly, we need to do the meshing. Then the next command is block mesh. Then the decompose part, which make the decomposition of in parallel from this simulation. So as we discussed in the previous slide when we presented the decomposition type or method in the OpenFoam, we had a simple, scourge, and hierarchical. Then we are doing the setup on the directories, and here only we're running the command for decomposition. You should pay attention when you are doing copy of the example. You can go to the directories of the example and select your method for the decomposition. For example, you can run 3 times with different methods, and you can see the different of these uh, computing time and also different of the result. Therefore, in the batch file, we are not doing anything regarding the decomposition method. It needs to be done from the directories. Then we run the simulation, which is based off the simple form in parallel. With command of the torch form, it will create the result. The reconstruct part also, we reconstruct the domain based of what we meet the decomposition. Then it will collect all information in the one domain and one result. And we can use the visualization with the command of the form to VTK, which is converted to visualize it, and we can use the paraview. Then this step here is presented here in this batch file, and you can use it. And I will share the original file on the canvas, and you will have access to use this batch file. So we will look to uh, the earlier system to run this OpenFOAM parallel. However, as I said at the time of the recording, because I didn't have access to the earlier, I will use Lumi to show you some section of the OpenFOAM directories. Okay, before doing the modification on the example for the batch file, let's present you some references for the OpenFOAM. It will be useful, and you can take a look if you're interested in the OpenFOAM, and maybe you are using it. Here there is a CFD direct. It has a good user guide, and usually it's updated with the new version. And you can see how some example you can run, and also regarding the parallel computing that we were talking. Here you can see section of the is in the content in the chapter 3, running application in parallel. Here you can see the information regarding the different decomposition as we talked about them, the simple, hierarchical, and scotch, and how they are working, and how you can run the decomposition command on the parallel, and you can see the result. We will present it in the batch file as we talked before. Also in the OpenFOAM wiki, you can see good information. There are some resources for tutorials from literature. For example, for the tutorials, you can see very different collections, and you can learn from them how you can use the OpenFOAM and with some example with setup. Regarding the methods that we talk in the decomposition method, we need to mention that selecting this method, it's affecting the performance and loading balance. Here there are some lists regarding the the method of the decomposition. For example, the simple, what type is it, and how it's working. It's based off the direction XYZ, and there is a pros and cons list of them. However, the limit of the application is working with the uniform structure. When we look on the hierarchical one, it's flexible than simple. We can work with this. It's working along one direction, and you can see list of the pros and cons, and mm, it's working better than simple. We can say. Scotch is working graphical based. It's topological. And dividing, in fact, the domain to subdomain, analyzing the cell connectivity, and trying to balance the load and minimize the communication between subdomain. So this is the pros and cons of it. And also we can mention when we have complex and unstructured mesh, it's better to use the Scotch approach. Now let's look on the uh, directives and the example for the OpenFoam parallel decomposition. I'm running this example on the Lumi because at this time that I'm recording, the Elia system is down, and it will working on a Monday. So I'm using Lumi system. As I said, the setup is same. Just here the initial condition determined on the batch file for the Lumi, and you will use the same setup for Elia. Let's look at the file that we have. Let's see. So we have the OpenFOAM folder. Let's see the directory of the motorbike. Again, we need to go to the motorbike. So here we can see the different directories that is available. As we mentioned, we had the zero directories. Here we can have the initial condition, we have the constant, and also we have the system. We can do the setup for the decomposition. Let's open the file and look at it. So here we have the file. As you can see, there is a different setup we used in this example here. We use one-time hierarchical Scotch, and let's open the Scotch one. We look on this file. So it seems we didn't use this one. Let's open another one. Here you can see the setup for the type of the uh, method it's used. Here we use the hierarchical, as we said, the hierarchical working along a direction. And here the number of the sum is specified. Then we need to specify the coefficient, which mean in which direction and how many numbers we need to specify in here, which is x, y, z, and we specify alongside which direction and how many number to decompose the domain of the problem. And in the same approach, we can specify the type here. We can write simple or a score, but how the coefficient will be different setup. So here it's how we can make the setup of the decomposition. The detail regarding how we can doing the setup for the OpenFOAM example, of course, it could not be covered in this one short lecture. However, I presented some resources. You can use them. And of course, you have access to Elia system. It has the OpenFOAM, and I will share the batch file. You can use it, and you can run it, and you can see how it's working on the Elia system. Then let's continue to discuss the effect that need to be pay attention for the setup of the decomposition when we are using the MPI with the OpenFOAM. So, what is the domain decomposition? Here, it's a simple visualization to see how there is a different approach to make the decomposition of the domain in the 3D of the simulation. As you can see in the both of these examples, there are 8 blocks which assigned to individual processor. But these decomposition for the domain is different. We can say in the left hand side we have a queue, but on the right hand side we have a column of the blocks with same domain. This is important how we select these blocks because it depends to the boundary condition. Sometimes it's required to make a block, or sometimes you need to get columns. So this is information based off the problem, and also it's effective with the uh, interconnection between the processor. For example, when we look at the cube one in the left hand side, we can see it has a two surface connected to a neighbor domain vertically and one horizontally up, so there are 3 surfaces. But when we look on the column one, there are 2 surfaces connected to neighbor domain, and there is no third one. In fact, fourth of the domain, the surface are connected to the boundary condition, not the internal connection. So this information about the boundary of the problem, boundary condition, and how we need to transfer the information between the domain is important to do the setup of the decomposition. Therefore, the decomposition has a step to use the MPI. In contrast to the previous setup for the decomposition, here also you can see the different setup of the blocks. Here the blocks only the internal blocks has 2 surfaces that they are connected to up and down neighbor subdomain. So this setup, as we said, is depend to the problem. But here, if you want to look on the setup, the steps to use the domain decomposition. In fact, in the beginning, we need to break up the domain into blocks or subdomain. Then it's assigned each block to the MPI processor. Therefore, we can make the modification and write the code to update the single block and providing a map of neighbors for each processor, insert the communication subroutine, and then adjust the boundary condition. These setup required to make the decomposition. This step when we are using the MPI is need to be done to use this capability, and also we need to mention that In the OpenFoam, these decomposition setup could be done from the decomposition block, and we can connect these decomposition to the MPI processor via setup. Uh, Therefore, it's not a decomposition based off the geometry. We need to look at the boundary condition, initial condition, and the geometry of the domain. Then we are able to make the decomposition. When we have unstructured meshing, also it's important, which in some places there is a much more uh, uh, concentrated of the fine domain, fine meshes, which get much more accurate solution for us. To emphasize the importance of the boundary condition here, let's have this simple description that in addition to knowing who is the neighbor, each process needs to know whether any of its boundary is in fact a physical boundary. This helping to avoid the programming error and also apply the boundary condition correctly. There are two cases of the boundary condition could be used, the periodic boundary condition and non-periodic boundary condition. We will determine what it means, these two different boundary conditions, and how we can apply them in the problem. When we are working with the periodic boundary condition, in fact, any blocks is treated as internal block. That means if we have a block at the end of the domain or subdomain which is at the end, it's assumed as other internal block. To apply these boundary conditions, we only need to define the correct math of the neighbors for each one. For example, here you can see example of the poster for the subdomain, for example, 12. Uh, to make a correct map neighboring, we can have the poster 0 as a neighbor for poster 12. Therefore, it make it a periodic boundary condition, and in fact, this term means all subdomain assumed as internal block in the domain of the problem. This is the simple definition. However, when we have different maybe boundary condition or especially about the geometry, maybe we need to pay attention more to this setup to apply the correct setup for it. In non-periodic boundaries, we behave different for the setup for the cursor. If we assume the same example that we have in the previous presentation, the previous slide, the cursor 12 doesn't has neighbor in the right hand side. So we should mention this that we say there is no information from the non-existing block. There is no block in the neighbor, so there is no information. We need to specify this information for block 12. The easy approach when we are using the MPI, we can use the MPI constant to handle it from the MPI proc null. And here you can see example in the blue block that how this setup is working to avoid sending or receiving data from a non-existent block. So this is the difference between the periodic boundaries and non-periodic boundary condition, and how we are dealing with especially processor of subdomain that they are at the end of the uh, domain, which they don't have a neighbor to get information from them. So here we ended with lecture 10, OpenFoam software and CFD application. In the end, there is a video and the link is available. I suggest you to watch it to see how the MPI is working. especially for this CFD application that we were talking about there. And in this lecture, you saw application practically of the OpenFoam and how it's working for the domain decomposition, and how we can also make a modification with the MPI. Especially, we talked about the effect of the boundary condition and how we can use the periodic modification and non-periodic boundary conditions. Thus, when we are using the MPI, we can make the efficient parallel computing for such problems. So thank you. We will continue in next lecture. Good luck.